the schedule for today, remember, we are not doing what our schedule says, class 17 today. We're going to wait and start that on Wednesday. So today's class will be class 20. So that's why your notes say class 20 today, even though it's only the 17th day of the semester. So the homework that will be due for next Wednesday will be class 20. For this week, it will be 15, 16, and 20. Now remember, 16 only has 2 problems on the entire homework, because most of the problems that you should be working on and making sure you complete are at the end of class lecture note 16, which we were working on in class Wednesday. So the book had 2 problems that I could kind of dig out, but really to be ready for any type of quiz or test, make sure you work through the lecture notes activity, okay? So today's class 20, just so you don't get confused, instead of 17. So homework that's due next Wednesday will be 15, 16, 20. Okay. All right, so let's take a look at today's opening quote. And Ian, do you mind shutting that door, please? Never mind. Okay, so the opening quote, Adam?
When 2 functions love each other very much, they share a special kind of algebraic operation.
I think you definitely outdid my first person. Yes, very good. Okay, so today we're going to be finding ways to create new functions from 2 or more functions. And one of those ways is to create new functions through our through our operations of addition, subtraction, multiplication, and division. So someone want to read what's in the beginning of what's in this box for us, Shane?
Let F and G be functions. The sum, difference, product, quotient functions instead of D.
So what do we think the D is representing here? D with this little subscript F, if it's coming from the phrase just before it. Domain. So the domain of F, and what does that symbol mean again? No, intersect, right? Because we're looking for the stuff common to both sets, to both domains. So the domain of F intersect with the domain of G. Another way to say that is what numbers are common to each domain. Okay, so this is how we're going to write it. If we're trying to write the sum of 2 functions at a particular value, or at any x, then we put f and g in parentheses with a plus, and then we put x after it in parentheses. And we define that to be f of x plus g of x. And similarly for each of the operations that follow. And we have to be very concerned when we do a quotient, because we have to make sure the denominator is defined for all, this quotient is defined for all numbers, and we got to pay particular attention to when g of x does not equal 0, because we can't divide by 0. So let's do some problems with combining functions through 4 basic operations. Okay, so we're going to let f of x equal x squared. And what kind of function is f of x equal x squared? What kind of function is that? What name could we give to that? Quadratic. And how about that's one of its classifications. And how about an even bigger classification than quadratic? Another class that it fits into, that all quadratics fit into, and all cubics, and all linear functions, and all quartics, and septics, and however far we want to go. What's the name for that big class of functions? Polynomials, right? So this is a quadratic function. It's also a polynomial function. Now remember, polynomial functions are your friends, because polynomial functions have really nice exponents. They don't have negative numbers for exponents, which means there's never anything in the denominator, and they don't have rational exponents, rational number exponents. So you don't have any like even roots or anything like that. So they're just numbers 0, 1, 2, 3, 4, 5, like that, all the way up. So the nice thing about about polynomial functions is what would the domain of a polynomial function look like? What's the domain of a polynomial function look like? Infinite, right? Well, what set of numbers is that? All real numbers, right. So the domain of F is all real numbers, which means all numbers on the number line. Okay, which we can write in interval notation like that. If we use our number line, we just write an arrow going in both directions. Okay. Now g of x isn't a polynomial because you have x plus 1 in the bottom. So you could write that as the quantity x plus 1 to the negative 1 if you wanted to. It's definitely not a polynomial because it has a negative exponent or it has your expression in the denominator. So does anybody remember what name we give to this particular function here? Rational, right. Wow, Shane. Woo, go. You go, boy. Rational function. Okay. Right, so now we have a little concern because with the rational function, we know that the bottom cannot be 0. So we have to look at what number will create a 0 in the denominator, and then we exclude that, and then our domain is every other number but that number, or sometimes it's more than one number. So what would be the value that's excluded from the domain of g of x? What number is excluded? Negative 1. So we know negative 1 would have an open circle, and so the domain is the set of all numbers to the right of negative 1 and to the left of negative 1, and this is how we represent it on the number line. How would we do it in interval notation? Anybody want to help me with that, in interval notation? Negative infinity. Okay, so we don't have to use less than, because with our interval notation, we go from the smaller number to the next number. So we could just put the negative 1 like this, okay, with a parenthesis. Then how would we finish it off? When? Negative 1 comma positive infinity parenthesis. We're missing one little thing. Austin, what's that? What's the U look like? What's it called? Union. Okay, now remember, this doesn't have a stem. A lot of you are putting stems on this, like you're in penmanship class, okay? There's no stem, it's just a U. It's no little stem. Okay? So now the domain for the both functions combined is what set of numbers do they have in common? So what set of numbers, so if you put this set of numbers on top of this set of numbers, what do they have in common? All numbers but what? All numbers but negative 1. So the domain of f intersect the domain of g is actually the same as the domain of g, because the domain of g has a restriction in it. Domain of f has no restriction. So the domain of g becomes their intersection. Okay, any questions on that, finding the domains? All right. So let's now add some functions up and subtract and divide and multiply. So f of g, the sum of f of g of x is going to be f of x plus g of x. Okay. So let's try it first with a number, just so we can see how we do this if we actually had a number for x. So f of 2 plus g of 2. So what would f of 2 be? Tara, can you help me with that? F of 2? That just means that I go up to my f function, and where you see x, you replace it with a 2. Yep, 4. Okay. How about g of 2? Can anybody help me with g of 2? Austin, want to help me with that one? So here's g of x, and you put a 2 in. Yeah. 1/3, right. 1/3. Okay. And now in order to add fractions and make a single fraction in the end, to make one single fraction, what must be true in order to add those two? To make it one single, what must I do? To add 4 1/3. Common denominator, right? They have to be like. Everything we add and subtract in mathematics has to be like. So I need to change 4 to, which is 4 over 1, to an equivalent fraction that has 3 in the denominator. So I multiply top and bottom by 3, and that's 12/3. So I get 12/3 plus 1/3, and that gives me 13/3. So there's my answer, 13/3. All right, so let's do it now for the general case for all x. So we want f plus g of x. That's equal to f of x plus g of x. So for all x, except one number, -1, wouldn't be included anywhere in here. So f of x, we're defining to be x squared, and g of x is 1 over x plus 1. So we have to do the same thing to this expression that we did up here. With 4, we changed 4 to 12/3 because our denominator there was 3. Our multiple of 1 and 3 is 3. 1 times 3. Here, x squared is sitting over a 1 as well, just like the 4 was. So we have to change x squared to an equivalent fraction that has x plus 1 in the denominator. So you do it exactly the same way you did with the 4. You start off with your x squared, and you say, what do I multiply top and bottom by so that I have something over x plus 1? So you say, well, to make 1 into x plus 1, I have to multiply by x plus 1 top and bottom. So you multiply top and bottom by x plus 1. So that's x squared times x plus 1 over x plus 1. And you notice, if you reduce this, you're right back to where you started. You're back to x squared. So I usually caution students and say, when you rewrite this now, just put LCD in the denominator for each one, so you don't go ahead reducing it and you're right back to where you started. That happens sometimes.
That's just like
Another method of, yes. Yeah. So you have x squared times x plus 1 over x plus 1, which we'll just call the LCD, the lowest common denominator, plus 1. So now you use your distributive property and you get x cubed plus x squared plus 1, and that whole thing is over the LCD, which is x plus 1. So there are our two answers. Put your arms around each one. There's no way you can do any reducing because there's no factors of x plus 1 in the top. Can't factor that top. Okay, so you say, I don't know if that's really the same as what we just did. Well, try it out. Here's your end result. We're saying that if you add f of x and g of x, this is what you'll always get regardless of what number you put in at the beginning. So we just put a 2 in and we got what for an answer? 13/3, right? So let's put a 2 in here. 2 cubed is 8 plus 2 squared, that's 12 plus 1. 13 matches 13. And then 2 plus 1? We're golden, right? Okay. So now let's try f take away g, the difference of these two functions, f of x take away g of x. Now, do you have to do a lot of work? What's going to be the only difference? Right here, look, here's f of x already simplified with the LCD, excuse me, already with the common denominator, and here's g of x, and we added them. So what's f of x take away g of x going to look like? Well, the same thing it looked like a minute ago. X squared take away 1 over x plus 1. But we've already figured out what x squared is as an equivalent fraction with x plus 1 on the bottom. It's x cubed plus x squared over x plus 1. And now I just take away x plus 1. So the only difference between these two is that instead of plus 1 in the numerator, I have a subtract 1. That's the only difference. Any questions on that, Mary? Yep, and that's why up here we have the domain. So in other words, you could take this domain and you could put it on every single problem here. That's the domain, that's the intersection of their domain. So we could, if we wanted to, take a little picture of that domain right here. And we could paste it. Ooh, we want to make it a little smaller than that. We could paste it under every single one of these. We could say, this is true for all x, and this is your domain. Okay, so you could paste that everywhere you go. Okay, everywhere. Copy, paste. Here it is. So you could put it at the beginning or the end. So you can clearly see -1 would make this 0, just like it would make this one 0. So that's the domain for all 4 of these. Okay, so how about multiplying and dividing? Well, multiplication is a lot easier. F times g of x. Notice we don't even bother putting in the dot. We know that if we put 2 symbols, 2 letters beside each other, that it means multiplication, right? So this means f of x times g of x. And multiplication is a lot easier than adding and subtracting because you just multiply straight across and you are done. Voila, there's your answer. Okay? No having to make common denominators, nothing. Now, one of my students in my first class said, isn't this when I do x squared times x plus 1 and 1 times 1? Is that when I do cross multiplication, she asked me? What do you say to that? No, why not? It's not an equation, right? If it was an equation with the special name of a proportion, in other words, if it looked like this, x squared over 1 equals 1 over x plus 1, and you were trying to solve that, you could use your cross products. You could multiply both sides by x plus 1 or just use your cross products and solve an equation. So that's what happens when you teach people when they're younger, these little kind of, I call that, well, it's just something to remember, but if you don't know why that works the way it does, then you just start using it indiscriminately whenever you see 2 fractions. This is multiplication. And multiplication is numerator times numerator and denominator times denominator. Okay? Because I remember over here, Sean, when we created an equivalent fraction, we had x squared times x plus 1.
Right, so okay, so that's
yeah, and then x squared times x gives me x cubed, and x squared times 1 gives me x squared. So I just skipped a step since we did that all over here. So in other words, the intermediate step would look like this, Sean. Shane, sorry. I know your name. I don't know why I did that. Well, I've never done it, but I guess I did it today. So this would be taking x squared and making it have the same denominator, Sean? Shane, making the same denominator, right? All right. So here's your foo-foo, x plus 1 over x plus 1. And now when I multiply x squared times x, I get my x cubed. And x squared times 1, I get my x squared. So the only difference between these 2 problems is instead of it being a plus here, it's just a minus. Any other questions before we go on to division? Anything else? Okay, how about division? Let's take a look at division. Okay, so we have f of x divided by g of x. And what was f of x again? X squared. And g of x is 1 over x plus 1. So how do you simplify that little monster? How do you simplify that? X squared divided by the fraction 1 over x plus 1. How would you simplify 4 divided by 1/2? What could you do? 4 divided by 1 over 2 is the same as what? It's an arithmetic problem, folks. Multiplied by the reciprocal, right? So division is the same as multiplication by the reciprocal of the denominator or your divisor, whichever way you like to think of it. So it's x plus 1 over 1. And now you just do your distributive, use your distributive property, you get x cubed plus x squared. and you're all done. Okay? Okay. So you don't look at the end result, because here it looks like your domain would be all real numbers. But remember, you could never put a -1 in at the beginning, because -1 would make that a 0. So you don't look at your simplified version. You look at it before it goes in. Okay? Any other questions before we move on to another idea of how to combine functions? Anything at all? Okay. You'll have maybe 3 or 4 homework problems like this. Okay. So composing functions, I'm not even going to define composing functions for you. I'm just going to tell you that there's another way to compose, to make new functions. And to make, the other way that you make new functions is by putting them in some kind of sequence, okay? And the output of one function is going to go into, become your input of your other function. And so we're going to start off with a biological function, 2 biological functions. So, want to read the first one for us, Buddha? Of person P. Okay, so I got to call it the mom function because, I can't pronounce ER because I'm from Boston. Okay, so that's what my students in the spring said. Just call it the mom and dad function, then you don't have to worry about your ER. But of course, I'll say mother, right? Mother function. Okay. How about this one? Glenn, how about that one?
Father function is biological.
All right, so what's the domain? What's the domain for these functions? What's the domain? It's not a number. Can't put numbers into, ask for the mother of a number and the father. So what's the domain? The domain is P. So what are legitimate values, are legitimate inputs for P? All human beings, right? Okay, all human beings. So in your groups, and this might take a few minutes, I want you to discuss what family member is represented by this right here, M, this is how you read it, M of F of P. M of F of P. What family member are we referring to? So see if you can figure that out. And when you do, put up your flag. Okay, so what did we come up with, Mary? The paternal grandmother. Paternal means on your father's side, right? Paternal grandmother. Okay, so let's try this with a person, and we'll do it visually here. Okay, so here's a little visual of M of F of P. So we're going to pick, let's see, we're going to pick Beth. Okay, so Beth is going to be the input. She's a human being that's been born and is actually living, but you don't have to be alive to do this. Okay, so Beth, what's the father of Beth? What's your father called? Chris. Father of Beth is Chris, right? So this, then I replace the father of Beth with the name Chris. Okay, the father of Beth is Chris. So Chris is the output of the first function. Okay, Chris is the output of F of Beth. Now Chris goes into the mother function. So Chris becomes the input to my function M. So now I'm looking for the mother, did I say it right? Mother of Chris, almost. And who's the mother of Chris? Cecile. Okay. Cecile. Okay. All right. So language that we use with this is we say F of P, we call that the inside function because It's the first function you're doing. You're first finding the father of P, whoever P is. So we call this the inside. And if you look at it, it's sort of like your order of operations where you go to your innermost parentheses first, right? And you do what's in there. So this is called the inside function. So F is the inside function. M is the outside function. All right. So what do you think, folks? Do you think we say 2 plus 3 is the same as 3 plus 2 and 2 times 3 is the same as 3 times 2? Do you think I can just switch those around and get the same thing? F of M of P, can I commute those and get the same answer? I saw one head go like this. Well, let's try it. The only way we're going to know is to try it. So here's the language that we've been talking about. Let me give you some new language. We read M parenthesis F parenthesis P parenthesis parenthesis as M of F of P. So as you read left to right, when you see a parenthesis, you can replace that parenthesis with the word of. M of F of P. Okay? We call this function the composition of M with P, or a composite function. Just like when you put a composition together for an English class, right? You take different ideas, you put them together, hopefully in a logical, sequential way so it makes sense, right? So the composite function is written this way as well. This is a new symbol for a lot of you. So that symbol, which looks like the same symbol you use for a degree, except for instead of it being a superscript, it's right in the middle of the two functions. That's a symbol that denotes composition, composite function. Okay. So we could back this up and do M with that little open circle F, you put it in parentheses, of P. And the way we define it is to first do the inside function on P and then the outside function. Okay. So let's try it in the other way. Let's see if the order matters. Mary says no, and nobody else did anything with their head. So let's see. What family member does F of M of P refer to? So try that at your seats, and we'll see if it's still the paternal grandfather or not. Oh, yeah. Is that what we got? We got paternal grandmother before, right? Sorry. Okay. What family member did we end up with this time? Maternal grandfather, right? Mother's father, right? Maternal grandfather. So does the order matter? Yes, absolutely. Okay, so M of F of P does not equal the composition of F with M of P. Written another way, M of F of P does not equal F of M of P. Okay, so that's something to put in a big box in your notes with stars all around it, that the composition of functions is not commutative. That's the word we use. That's the mathematical property. In other words, the order matters. Okay, so let's take a look at doing some composition with functions that involve real numbers instead of people. Okay, so let's take a look at that. Okay, so again, this is just a repeat now, but instead of the functions called M and F, we're going back to our generic functions, F and G, little f, little g. So it almost looks like the word fog. F with the little open circle, G, is defined by this equation where x goes into G first, and then G of x goes into F. Now, what we have to pay particular attention to is how to do the domain of a composite function. That's going to be a little interesting, but think about it. X has to go into G first. So X has to be in the domain of G. Okay, so right down here, here's our first function G. So X goes into G. So X must be in the domain of the G function. What comes out? The output is called G of X. That then becomes the input of your F machine. So not only do you have to worry about the domain of G, you have to say, what does the range of G look like? It's called G of X. That's going to be the domain or the input for F. So G of X must also be in the domain of F. So you've got a little bit of work to figure out domains for composite functions. Sometimes they're pretty simple, especially if you have polynomials. And sometimes they can be complex if you have rational functions or even root functions or combinations of the two. So let's take a look at some real number functions now. So the first function, these are the ones we worked with at the beginning of the hour. F of x is x squared and g of x is 1 over x. So let's compose f with g. So our definition, f composed with g of 3 is f of parenthesis g of parenthesis 3. And then we close our parentheses. So the first thing we do is we put g of 3, we figure out what g of 3 is. So I say over on the side of my paper, I say g of 3 is 1 over 3 plus 1, which is 1/4. So where I see g of 3 inside those parentheses, I replace it with 1/4 because that's what g of 3 is. So now I get f of 1/4. Okay, so I just replace g of 3 with the value of g when x is 3. And the value of the function g when x is 3 is 1/4. Now, to finish this off, I have one more step. I have to say, okay, now I'm going to put 1/4 into my f function. So what does f of x tell me to do? Take any input and square it. My input now is 1/4. So I square 1/4 and I get 1/16. And that's my answer. Okay? Any questions on that? So I'd like you at your seats to try g of f of 3, the composition of g of f of 3. See what is 1/10, right? G of f of 3. First we put 3 into the f function. So here's another way to write, well, we'll do this for the next one. So f of 3 off on the side of your paper is 3 squared, which is 9. So we get g of 9, and now we do 1 over 9 plus 1 is 1/10. Okay. Now, how do we write the general expression for the composition? Well, that's instead of picking a specific value for x like 3, as we did here, we find the expression for all x. So this equals f of g of x. So what that means is f is your outside function. So you're going to be squaring something. That's the last thing you're going to do. You're going to square something. What goes into f is g of x. So here's what I'm squaring. I'm squaring g of x. Now replace g of x with what g of x equals, which is 1 over x plus 1 square. I don't know. I'm saying that because I don't know how far my math lab wants you to take this out. So I'm going to show you the whole shebang out, okay? Just so you can see it. So you use your exponent properties. Your exponent property says to square the numerator and to square the denominator. So the denominator is a binomial, so be careful. 1 squared is 1, and then you have x plus 1 squared, which is x plus 1 times x plus 1, which is x squared plus 2x plus 1. So I'm not sure until you do the homework, I could look at the homework later, which of these forms my math lab wants it in. But it's only going to take you another 5 seconds to go from here to here. I'd be more okay with the middle one than this one. But if you leave it here, I don't know. I have to think about it. I'd want to make sure you know how to use your exponent properties. So I'd want to see at least this here. Okay. Now, I don't know if my math lab wants this one or this one, but we'll figure it out. I'll look it over the weekend. Okay, and this question came up in my 840 class, and I said, every opportunity I get to square a binomial, to ingrain that x plus 1 quantity squared is not x squared plus 1, the better. And one of my students said, thank you for doing that, because he said, I still do x squared plus 1. So I will do this on as many occasions as I can. Okay, so let's do g of f of x. So I'm going to be the writer. You tell me what to write. G of f of x, I'll start us off. Looks like this. So where do I go from here? So I'll take your direction from here. G of f of x. So you guide me. You want to start us off, Adam?
Sure. 1 over x plus 1.
1 over x plus 1?
Sure.
That's what g of x is. All right, so I'll put that underneath. Okay.
Now the x's you substitute.
Okay, so I substitute f of x, because that's what's going into the g function. And now f of x is x squared plus 1. And that's your answer. There's no simplification of that. So g of x is your outside function. It's 1 over something plus 1. That something is being called f of x. And now we replace f of x with its meaning, which is x squared. Any questions on that? Okay, let's figure out the domains now. What's the domain of this composite function? So here's my g machine. Here's my g function. And here's my f function. Okay, so let's put these over on the side here. G of x is 1 over x plus 1. And f of x is x squared. So what is allowed to go into my g machine? What set of numbers? What is the domain for g? What's the domain for g? Everything but -1, right? We talked about that at the beginning of the hour. So it's the union of these two sets. So that's what can go in to g. What's going to come out of g? Well, a bunch of different numbers called g of x. They're going to be positive and negative numbers, okay? So now we have to say, okay, do we have to worry about what goes into f? What goes into f? What's the domain of f? Which is x squared. What'd you say? Whatever you want. That's good. All real numbers, right? So that's -infinity to infinity. So anything that comes out of g of x is going to be allowed to go into f of x, f of g of x. Okay, so since -1 couldn't go in to begin with, it's never going to come out being a negative. Ooh, wait a minute. Even if it came out being a -1, that's okay, because -1 can be squared. So -1's never going to be allowed to go into g, and that's going to be the only number that is restricted from this composite function. So the domain of f composed with g is going to be -infinity to -1 union with -1 to infinity. Because x has to be in g, and then g of x has to be in f. But there's no restrictions on f. So it's just the initial restriction. Okay, so I'd like you to do the next ones at your seats together. And then I'd like you, after I check, I'd like you to work with this graph. Okay, so now instead of there being 2 equations for f and g, you have to pluck the outputs out from the graph. Okay, then you have a series of problems to do that will take you from all of this. You'll be very busy for the next half an hour. So start with this 6, go to 7, try a few at 7, and then try to get your activity done, or at least half done. Okay.